In our previous example, we talked about health insurance, and we partitioned the sample space into those Americans who do have health insurance and those Americans who don't have health insurance. And then for these two possible outcomes, we assigned probabilities based on the data. So we calculated proportions, and we said, well, the probability of having health insurance is 0.88, and the probability of not having health insurance is 0.12. Now, one thing to keep in mind is that we need to be careful with probabilities, because these probabilities are based on the data at hand. So here's an example of probabilities. And the fact that you can calculate probabilities for just about everything, but that doesn't mean that the probability is valid, because it depends on some set of data or some other sort of set of observations. So here's this guy, and this is an actual news article, and he said he basically calculated the probability of him finding a girlfriend. And so he says the conclusion is that girlfriends are harder to find than aliens, says this math nerd. And in fact, he calculates the probability of him finding a girlfriend, this is real, is basically near zero. And so he's a British guy, and he says the probability of finding love in the United Kingdom is only about 100 times better than the probability of finding intelligent life in our galaxy. So it's almost nothing in terms of the probability it calculates. Now, a recent news article actually showed that the same guy, this math nerd, he got married. So even though he said that the probability of finding love for him was 1 in 285,000, he said, well, he actually did find somebody, and now he's getting married. And then, of course, his conclusion is that most people work out the equation and find their partner eventually. But this raises the question, where do these probabilities come from? For the health insurance example, we gathered this set of data. This math nerd, he basically calculated the probability of him finding love in the United Kingdom based on various statistics from the United Kingdom. But we have to be careful. You can calculate some probability, but that doesn't mean that that probability is accurate or even valid, because it depends on some property of the data set. Maybe your data set is a weird sample, or maybe you're selectively picking out different observations on which to calculate your probabilities. And this raises the question, where do we get probabilities? Where do they come from? Well, for the health insurance example, we gathered it from data, but for that British guy, he was really calculating the probability of a white male PhD student in his 20s living in the United Kingdom in 2010 of finding a girlfriend. There are, in general, three main ways of calculating or obtaining probabilities. So the first way of really thinking about probabilities, where they come from, it's the experimental or empirical origin or approach for calculating probabilities. We can also think about probabilities in a logical or classical sense. When most people first learn about probability, they implicitly learn that probability in terms of the sort of logical or classical approach. But we can also think about probabilities as coming from some subjective or personal preference. The good news is that no matter where probabilities come from, the rules for working with probabilities, the three basic rules that we've covered, as well as rules that we'll cover in just a bit, the rules remain the same. So working with probabilities, it remains the same. However, whenever you see a probability, you just say, well, where is it coming from? Where do we get these probabilities? The first approach is the empirical approach, sometimes called the experimental approach. So the idea behind the empirical approach is you obtain probabilities based on some set of data. So the probability is calculated based on some observed frequency of an event. So when we calculate probabilities based on a set of data, each observational unit, each row of interest, it can be viewed as a different trial or repetition of some event. So the probability of an event is the number of trials in which the event occurs divided by the total number of trials. To put it another way, it's the number of rows or observational units in which that event occurs divided by the total number of rows or observational units of interest. Now, there's several problems with really calculating probabilities from this empirical way. it's a very common way to assign probability values. It can be misleading though, because if you have a small set of observations, meaning if you have a small set of trials, then really these probabilities might be misleading. To sort of think about it in a trivial way, you could collect a very small data set based on flipping a coin 3 times. So suppose you flip a coin 3 times and you obtain heads 3 times. So this would be kind of a small data set. It's a little empirical based set of data. And so each row is a different trial. And so you might say, well, we have 3 rows, we have 3 observational units. And based on this little set of data, we say, well, the probability of obtaining heads is 1, because we had 3 trials and we had 3 trials with heads as the outcome. So you can see that the empirical probabilities, it's based on your sample of data. To put it another way, a small sample size, or a sample size that is sort of off in some way, it's not really a representative of some population or other group. The idea is that if you have a small sample, it's really equivalent to some kind of anecdote. So you might say, I know 3 people who smoked every day and lived well past the age of 90. That's equivalent to flipping a coin 3 times and saying, well, okay, I got heads each time, all right? The probability of obtaining heads is 1. So empirical probabilities, they're only as good as the data on which we use to calculate those probabilities. Another way of thinking about where probabilities come from is this logical or classical approach. It's based on a slightly different calculation. The probability of some event occurring, it's the number of outcomes in which that event occurs divided by the total number of possible outcomes. So one assumption with this logical approach is it's based on the requirement that each of these possible outcomes, they're equally likely. So you flip a fair coin, it's equally likely to get heads or tails. You roll a die, it's equally likely to get 1, 2, 3, 4, 5, or 6 when you roll that die. So this is an example. The probability of heads, it's 1 divided by 2, it's 0.5. In terms of rolling a 5, you roll a fair die, the probability is 1 divided by 6, because there are 6 possible outcomes, and there's 1 outcome out of that 6 in which you would roll a 5. There are limits with this logical or classical approach to assigning probability values to some sample space. It's straightforward, but it's only really applicable when you're dealing with certain contrived examples. So basic games, gambling, card games, roulette wheels. It's because it requires that the probability of each possible outcome is the same. Most random phenomena that we study in the social sciences and humanities, they don't resemble card games or dice games. So this logical approach, we don't typically use it to obtain probability values. The third way to think about probabilities, where they come from, is a subjective approach, a personal approach. The idea is that for some event, you assign a probability value based on your own personal belief or subjective judgment. So with this approach, you don't even need evidence. You don't even need any set of data or any sort of logical criterion to assign some probability. You might say the probability of finding a girlfriend for a PhD student living in the United Kingdom is 0.2. Right? It's your own personal belief, and that is a way of assigning probabilities to some events. Of course, there are clear limits to the subjective approach. You can base it on evidence, but not necessarily. So it could be wildly off base if you're uninformed. So you might say, well, the probability of, here's an example. A lot of people are afraid of flying, and in some ways they're saying, well, the probability of my plane crashing when I'm in it is 0.3. A lot of people use subjective probabilities, whether they realize it or not, and it may not be based on actual set of data, actual processes in the world around us. Another problem with the subjective approach, besides the fact that it might be based on your own biases with very little evidence or no evidence at all, is that by assigning subjective probabilities, it might violate logical probabilities. So you flip a fair coin, and you might say, well, the probability of obtaining a heads is 0.7. And in fact, you actually do see this. There's something called the gambler's fallacy, where people think that, okay, if you flip a fair coin and you get heads 10 times in a row, a lot of people think that you are more likely to get tails the next time. When in fact, if it's a fair coin, each flip is a different trial. It's an independent trial. It's an independent event. So the flipping a fair coin is still 0.5 each time, but people might think in terms of subjective probabilities and say, well, because I got 10 heads before, now the probability of getting tails is higher. It's 0.7. Well, that's subjective probability is false. It violates logical probabilities. So the things to know for what we've talked about so far is that probabilities are just a way of saying how likely or unlikely an event is to occur. Probabilities can also be expressed as odds, but for this course, we're really going to focus on probabilities ranging from 0 to 1 inclusive. When we talk about where probabilities come from, we can think of probabilities as coming from a set of data, meaning a set of observed trials or repetitions of some event. We can think about probabilities coming from a logical way in terms of the structure of a set of possible outcomes. Or we can think about probabilities as coming from subjective beliefs or personal viewpoints. Often, for this course, we will talk about probabilities gathered from a set of data. The great news is that no matter where your probabilities come from, the basic rules work the same. The sample space must be collectively exhaustive and mutually exclusive. The sample space must equal 1. Probabilities must be between 0 and 1 inclusive, and so on and so forth. So with this, we will conclude our discussion of the basic rules of probability.